Hello, welcome to 5.3, inverse functions. Now, in your pre-calculus days, and maybe even in your Math 096 days, or whatever equivalent you took, you did inverse functions then. And you've done inverse functions in pre-calc part 2 and so on. Now we're going to talk about inverse functions and then extend that to the calculus portion. Okay. So inverse functions. Definition of an inverse function. A function g is the inverse function of function f if f of g of x equals x for all x in the domain of g. And get this, g of f of x equals x for each x in the domain of f. And so that should actually be very familiar. That's kind of what we learned at the end of inverse functions. The function g is denoted by f inverse. G is the inverse. F inverse does not mean 1 over f. So if g is the inverse of f, or vice versa, then the graph of g will be the graph of f reflected across the line y equals x. So example 1 says show that f and g are inverse functions, analytically and then graphically. Let's fill this up a little bit. There we go. Okay, so for part A, what we want to show is that f of g of x equals x. So that's going to be 3 minus 4 times g of x. So what I did, I put g of x in place of the x and the f. That's 3 minus 4 times quantity 3 minus x over 4. You probably see right off those 4's divide out. So that's 3 minus the quantity 3 minus x. That's 3 minus 3 plus x, which is just x. So that one worked. Now let's look at g of f of x. That's going to be, here's our g, 3 minus f of x over 4. That's 3 minus, now what's f? F is 3 minus 4x over 4. That's 3 minus 3 plus 4x over 4. That's 4x over 4, which is just x. So analytically, we've shown that these are inverse functions of each other. Graphically, but here's the line right here. This is the line y equals x. This is the graph of g of x. I'll take it back. This is g of x here, and this is f of x. The negative 4 is pretty steep. And we see they are reflected across this line here. Across the line y equals x. Okay, let's go on to Theorem 5.6. The reflexive property of inverse functions. The graph of f contains the point AB if and only if the graph of its inverse contains the point BA. So that's how they're reflected across the line y equals x. And we have the horizontal line test. Remember the vertical line test for functions? Now we have the horizontal line test. A function f has an inverse function, so a function has an inverse that's also a function if and only if every horizontal line intersects the graph at most once. We also call that 1 to 1. A function f is 1 to 1 if for x1 and x2 in its domain, f of x1 is equal to f of x2. So that for every x value there's a unique y value, for every y value there's a unique x value. That's what that says. Theorem 5.7. The existence of an inverse function. A function has an inverse function if and only if it is 1 to 1. So you can restrict the domain of a function like a parabola, so you only have half of it, so you'd have 1 to 1. If f is strictly monotonic on its entire domain, then it is 1 to 1 and therefore has an inverse function. So this should be a then there. So that means if it's strictly increasing or decreasing on its entire domain. Let's go on to example 2. Use the derivative and a graphing utility. I have the graphing utility here. To determine whether the function is strictly monotonic on its entire domain and therefore has an inverse function. So f of x equals natural log of x minus 3. Now the domain for this right off is going to be x is greater than 3 because natural log has to be only positive, so x minus 3 has to be positive. Adding 3 to both sides, x is greater than 3. Now f prime of x is going to be 1 over x minus 3. So for x being greater than 3, 1 over x minus 3 is always positive. That means it's always increasing, and we can see that here with the graph. It's always increasing. So it is 1 to 1, and it will have an inverse. And the next one, f of x is cosine of 3x over 2. And we see that here. Nice cosine curve there. Now our f prime of x is going to be negative sine of 3x over 2 times 3 halves. So that's going to be negative 3 halves sine of 3x over 2. Now sine is not always increasing, not always decreasing. If we have not restricted the domain of the function, like to say here, that would be a restricted domain, then it's just decreasing. But then it increases again, then decreases, increases, decreases. So this is not monotonic. It's not 1 to 1. So the inverse is not a function. Unless we restrict the domain. We could draw a horizontal line here, and it's going to hit it more than one time. If we draw horizontal lines in this previous one, it only hits it one time. Okay, how do we find the inverse of a function? Hey, we have some guidelines for that. Guidelines for finding an inverse function. First, use Theorem 5.7 to determine whether the function given by y equals f of x has an inverse function. Second, solve for x as a function of y. X equals g of y, which would be our f inverse of x. I should say that'd be like f inverse of y. Interchange x and y, the resultant equations y equals f inverse of x. Define the domain of f inverse to be the range of f, and verify that f of f inverse of x equals x, and f inverse of f of x equals x. Example 3 says find the inverse function of f. Graph f and f inverse. Describe the relationship between the graphs. Okay, so if we say y equals the square root of 4 minus x squared, and we're going to solve for x, probably in your pre-calculus days you swap the variables and solved. Here we swap at the end. We solve for x equals whatever first, and then we swap. So y squared would be the square root of 4 minus x squared squared. So y squared is 4 minus x squared. Subtracting 4 from both sides. Y squared minus 4 equals negative x squared. 4 minus y squared equals x squared. So x would be plus or minus the square root of 4 minus y squared. But we've got to look at, it's the same for x being positive. That would mean also then for y being positive, or 0. So we'll say x is the square root of 4 minus y squared due to the domain. And y would be, if we swap the variables, square root of 4 minus x squared. So f inverse of x is the square root of 4 minus x squared. Now what's interesting here, this is what we started with. The function is its own inverse. And if we graph it, what is this? This is a quarter of a circle. And it is the reflection of itself across the line y equals x. So f of x is its own inverse. Interesting that way. Okay, I'm going to go on to the next page. Example 4 says, show that f is strictly monotonic on the given interval and therefore has an inverse function on the interval. Our f prime of x is negative cosecant x. So on the interval from 0 to pi, what do we have? It looks something like this. Now this is the graph of f prime of x. What we're showing here is that the derivative is negative. It's below the x-axis for the entire interval. And with the derivative being negative, that means it's a decreasing function on the interval. So I know this graph increases and decreases, but the point of this graph is it's the derivative. And our derivative is negative. It's below the x-axis. If you recall from chapter 3, a negative derivative means it's a decreasing function. So f prime of x is less than 0, so it's a decreasing function. I'll say f is a decreasing function on the interval from 0 to pi. So f is strictly monotonic and has a derivative. I'm going to go on to the next thing here, Theorem 5.8. Theorem 5.8, continuity and differentiability of inverse functions. Let f be a function whose domain is an interval, I. If f has an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse is continuous on its domain. So if f is continuous, the inverse is continuous. If f is increasing on its domain, the inverse is increasing on its domain. If f is decreasing on its domain, the inverse is decreasing on its domain. And if f is differentiable at c, and f prime of c is not 0, then f inverse is differentiable at f of c. Well, I say f of c because then that's the range from the f function that plugs into, that becomes the domain for the inverse. Theorem 5.9, the derivative, this is a cool one here. The derivative of an inverse function. Let f be a function that is differentiable on an interval I. If f has an inverse function g, then g is differentiable at any point x for which f prime of g of x is not 0. Moreover, g prime of x is 1 over f prime of g of x, as long as f prime of g of x is not 0, because we cannot divide by 0. So what is this saying? G prime of x is going to be 1 over f prime. So you wouldn't have to find g. You could find its derivative at a specific point by doing 1 over f prime of g at that value. Okay. Example 5 says, find f inverse prime at a, so we're using the previous formula, for the function f and the given real number a. Here we have f of x equals 1 over 27 times x to the 5th plus x to the 3rd, and a is negative 11. So what we're talking about, f inverse at a. So we know it's going to be a comma negative 11. See, a would be the the domain, the input for this function. So a negative 11 means this function produces the negative 11. I'm sorry, let me back up. A is going to go in here. That means it's going to be part of the, for f of x, the point is some point c comma negative 11, because that's the output. For the inverse function, the negative 11 is the input, and it'll produce a c. So we're looking at f of c is going to be, if we plug c in to this, we'd have 1 over 27 times x to the 5th plus x cubed. And that's going to be, I should say c to the 5th and c cubed. And that should be negative 11. Now if I want to solve this, we have 1 over 27 times c to the 5th plus c cubed equals negative 11. If I multiply both sides by 27, c to the 5th plus c cubed is negative 11 times 27 is negative 297. If we bring it over, c to the 5th plus c cubed plus 297 is 0. Now I can take my handy-dandy calculator. There we go. So here's my calculator, my TI-89. Turn it on. If I go to the F through F2 is what I want. I want to solve an equation, or we can do finding zeros. I think I'll go with the zeros one. And the formula was C. I'll go with X to keep it easier, to be consistent with this calculator. X to the 5th plus X to the 3rd plus 297, comma, we're getting zeros for X. And it tells me it just shut off. Does that mean my batteries are not good? You must not like what we just did. Okay, well, I have the number written down. Okay, well, let's go back to what we're doing. Calculator's not a happy calculator. The C value that we come up with, C equals negative 3.06. So F prime of X is going to be 1 over 27 times what? This derivative up here would be 5x to the 4th plus 3x squared. So we have our derivative. We know the C value, it gets to be plugged in, because now we're going to go with F inverse prime of negative 11, of this negative 11, that's our A, is going to be 1 over F prime of F of negative 11. Sorry, F inverse of negative 11. Well, we know F inverse of negative 11, that produces C, and C we found to be negative 3.06. So this is really saying 1 over F prime of negative 3.06. See this right here, this is our negative 3.06. That's going to give us 1 over 1/127th, because I'm doing the derivative now. The derivative is in the denominator, times 5 times negative 3.06 to the 4th plus 3 times negative 3.06 to the 2 power. And that's going to be 0.05788. So I must stress on this, the 11, the negative 11 was output from f of x, and that's why we had to go back and solve to find c. What input for the original function would give us negative 11 as an output? That number gets plugged in down below. So I did not find the inverse function here. I used this formula up here and used the first derivative and all that to find the derivative of the inverse at a certain point. I'm going to go on to our last page. It says, find the domains of f and f inverse. Find the range of f and f inverse. Graph f and f inverse and show that the slopes of the graphs of f and f inverse are reciprocals at the given point. Didn't say negative reciprocals, so they're not perpendicular necessarily. Okay. So for the first one, our domain is going to be negative infinity to infinity, and the range is negative infinity to infinity. For the inverse function, same thing. Domain, negative infinity to infinity. Range, negative infinity to infinity. No big surprises there. That's parts A and B. Now for C, it says graph f and f inverse, and I have that down here on a graph. We saw this earlier. This is one of the first things we did. So here's the graph. There's our C. Now for part D. I shouldn't go that high. Let's go D here. So show the slopes of the graphs of f and f inverse are reciprocals. Excuse me, f prime of x. Remember our f of x was 3 minus 4x. So f prime of x is negative 4. Now the f inverse of x was 3 minus 4, no, 3 minus x over 4. So the inverse, derivative of the inverse is going to be negative 1/4 x. So our slope in this, sorry, just negative 1/4. Our slope in this case is negative 4. In this case, it's negative 1/4. Negative 4 is equal to 1 over negative 1/4. They are reciprocals of each other. Okay. And with that, we'll stop on 5.3. Hope this makes sense. Inverse functions, took a little bit of a step into calculus with that. Okay, send me your questions. Talk to you later. Bye.